Hello, welcome back. Enrichment, integration and discussion on a very difficult integral. I've done an easier version only the other day, but this one is the souped up version. It's the integral from 0 to 1, bracket 1 plus alpha x times the square root of 1 minus x squared, all in the denominator with respect to x, from 0 to 1. This parameter or constant is numerically less than 1, and we have to actually come up with this answer. This is the final answer that we got to get it to. Arc cos of alpha over the square root of 1 minus alpha squared. Okay, let's pause the video if you want to have a go at it, and then see how far you take it. You should be very glad if you manage to actually get it to the very end by yourself. It's actually quite lengthy, this one, so it's going to be quite a long lecture. Okay, let's get going. And the first thing that I'm going to do is I'm going to use a substitution. The kind of answer that I'm seeing in there, it's got our causes. It's going to be a trigonometric substitution. X is sine theta, or you can put cos, but I prefer a sine. Dx is the cos of theta d theta. And limits, in fact, the substitution, I have said it many times before, is not this one. We write like this for convenience. It's actually theta is the arc sine of x, and the limits will convert 0 and 1 will map into 0 and pi over 2. So let's convert our integral. The first step is actually quite nice. There's nothing really kind of obvious. Pi over 2, 1 plus alpha sine theta. I hope I don't make mistakes today, because I had 4 lessons already today, and this is my third filming of the day as well. It's very late. I'm trying to get a few videos done so I don't have to film over Christmas. That's 1 minus sine squared theta. There's my numerator. I'm going to put that on top. Cos theta. Let's put the d theta there, and of course this will go, and we have a very straightforward integral to do. 0 to pi over 2, 1 over 1 plus alpha sine theta d theta. How do we do this particular integral? The standard way that most students will be going for is what is known as the little t identities, or the, I don't even know how to spell Weierstrass substitutions. It's the tan half angle thingy. I call it little t. The little t identities. And those who are involved in integration an awful lot, and they keep saying that you should know by heart these kind of things, and unless I put the sine alpha, it should be sine theta there. See mistakes already. You should know this, unless you're being asked to prove before you use, for example, something like this. If you use the substitution, t is equal to the tan of theta over 2, your sine will be, sine of theta will be 2t over 1 minus, plus t squared there, and your dt, or rather your d theta, is going to be 2 over 1 plus t squared dt. These are all standard results. If you needed the cos, if there was a cos in there, the corresponding one, it would have been 1 minus t squared, 1 plus t squared. But I'm not going to do it like this. I did the easier version of that the other day. It was actually 1 over 2 plus sine theta with exactly the same limit. It was the same integral, only an easier version, far easier compared to what we're going to face today. This is exactly the same thing. If we factorize the 2 on the denominator, this will become, of course, a 1, and a half will come in there. And of course, it was the integral that we're doing today, where alpha is, of course, a half, and we have also a half at the front. That's just the constant, doesn't really affect the integral in any way. And I showed the little t substitutions, but I also did show a little manipulation, which in fact, that's how I'm going to do the integral today, because I just want to show you different kind of things that you can do, and some tough, not substitutions, manipulations and recognitions. I think it's more important than just taking the easy option for this one. Okay, so little t identities will work for this particular one. Still a lot of work, but I'm going to do it differently. So this is now how I'm going to proceed. All right, 0 to pi over 2. Next thing, 1. I'm going to create in there a double angle in sine and a double angle in theta over 2. So it's going to be 2 alpha sine theta over 2 cos theta over 2. That's basically using the sine double angle. Of course, sine 2a is equal to 2 sine a cos a, where a is in fact theta over 2. 1 on the top. Before I do anything else next, I just want to say what the little, what's the objective. This is actually, in fact, the little t identities without using the little t identities. It's just a clever way of manipulating. In fact, you do not need the little t identities for anything. I might do a lecture where I might show you 4 very easy integrals that normally will be done with a y-stress substitution. I'll do them without y-stress to actually show you how they're done. And if you manipulate, your objective is this. Is to create an integral where your top is going to be a sec squared of theta over 2, and your denominator a function of tan of theta over 2. Usually will be, for this type of integrals, there'll be arctans, but I have seen logs, I have seen other functions, I can't quite remember now. So this is basically the objective and what I'm trying to create in there. The little t identities actually take care of that. That's what they're doing. So what I'm going to do next is the following. I need to create a sec squared. I'm going to create the x sec squared of theta over 2 by either multiplying top and bottom by this or dividing top and bottom by cos squared of theta over 2. Of course, it's exactly the same thing. I'm just doing it wherever it suits me. I see it as multiplication. Wherever it suits me, I see it as division. So this is now the same integral. The top will become sec squared of theta over 2. That's exactly the same, multiplied by exactly the same quantity. And this time, rather than putting a sec squared of theta over 2, I'm going to think of it as dividing by the cos of theta over 2. So this will cancel me this, and it will create a tan there. So plus 2 alpha tan of theta over 2. And of course, my d theta. Not quite there. I've got my sec squared on the top, but at the bottom I don't have a function of tan of theta over 2. I've got the sec squared. That's not a problem. Of course, 1 plus tan squared is equal to sec squared. So I'm going to use standard trig identities, 0 to pi over 2, and this is going to give me 1 plus tan squared of theta over 2 plus 2 alpha tan of theta over 2, and job is done. I wish. Well, the job is done to actually get to this form, no problem, but we're far from the answer. So let's see what we can do next. This is, of course, I'm going to complete the square there because that's going to be some kind of arctan. So I've got a tan square there and I've got a tan there. So 0 to pi over 2. Completing the square there, I'm going to get a tan of theta over 2 plus alpha. That's on the denominator, all squared. Have a look what's happening now. When I square that, I'm going to get a tan squared. Multiply together and double, I get this. And then, of course, I get a plus alpha squared. So minus alpha squared. And then, of course, a plus 1 that was already there. So I'll write it more compactly. And is this an arctan is the question, and the answer is yes it is, because let us note that this quantity here is positive, because let me just rewrite it first of all. So we can actually see it is positive because of the condition we got in there. So we got the tan of theta over 2 plus alpha all squared. I hope the board is visible there, plus 1 minus alpha squared sec squared of theta over 2, and I'm going to put the d theta on the top because I have no room. And this 1 minus alpha squared is definitely positive, and because this is going to be some arctan, I'm going to square root it because of course it is positive, and then square it. Now, are we doing enrichment? I think we are. Do we do another substitution from there? I don't think so. Why is that? It's because we're very hard. And because we're very hard and very brave, we're going to integrate that at sight. This, of course, comes from differentiating. I hope you can actually see it. The integral of 1 over, let's use it in u squared plus a squared du is, of course, 1 over a arctan of u over a. In your formula booklet, we should all know this from further maths. Here I claim what produces something which looks like that. That's the whole point of all of this, is I differentiated. I'm not putting the constants. I will adjust the constants in a second. I need to differentiate to get this quantity, d by d theta of the arctan of the tan of theta over 2 plus alpha over the square root of 1 minus alpha squared. It will produce all these bits, including, of course, because when we come to the change, trying to differentiate the tan, this numerator, we'll get, of course, the sec squared of theta over 2. If you cannot see it, I'll try to explain better, but this is actually very difficult, and I don't know if I'm good enough to explain. I might be good enough to do it. Sometimes with very hard stuff, it's kind of difficult to actually make somebody else see what you see. Okay, let's start the integration, and maybe you can see it once I integrate it. This is equal to, I'm leaving some space at the front, the arctan, and the argument of that is going to be the tan of theta over 2 plus alpha, as I'm seeing it here, over the square root of 1 minus alpha squared. Oops. Close the square root. And of course on the outside I have 1 over a, that's this bit here. So that's 1 over the square root of 1 minus alpha squared. Now I need to check for any other change. So when I differentiate that, I will get this, I will get this, and I will also get rid of this bit that's just stuck at the front. But I will also produce, when I come to differentiate this quantity, a tan theta over 2 will differentiate to sec squared of theta over 2. All good, that's there. That's the whole point why this works. But it also produces a times a half from the chain of theta over 2. So I need to take care, so from the differentiation, a times a half. And when I integrate, of course, I need to divide by half. And rather than writing times 1 divided by half, it's the same as timesing by 2. And I'm going to write it here. This I claim is in fact, and we need obviously evaluation brackets, from 0 to pi over 2, is this integral. You can actually verify it by differentiating it. Just take this quantity. Remember, of course, these quantities are just constants, all of this. The only variables, of course, your theta. If your differentiation is good, just differentiate that and see if you're going to get, of course, this quantity, or this, of course, exactly the same. Okay, so integration is done. Evaluation next. Looks a bit scary still. Let's pull this on the outside. 1 minus alpha squared. And let's put in our limits now. Theta is pi over 2. 90, 45. Tan of 45 is 1. So we're going to get the arctan of 1 plus alpha over the square root of 1 minus alpha squared. Minus, is the lower limit 0? No, it's not, annoyingly. So that's the arctan. When we're putting 0 in this, unknowingly we got this plus alpha. This will die, but we got an alpha over the square root of 1 minus alpha squared. So of course now integration has finished, evaluation has finished. but the question hasn't finished. We're still a long way, and me personally, I'm more frightened now of this part than I was from the integration. My integration is decent. Now trying to manipulate this to look like this. Definitely, I can't just say I finished the question. First of all, the question is a show. So, and depending on how hard or how involved it is, there'll be quite a lot of marks if it was on an exam. Of course, do not panic. This will never ever come in a standard exam. I don't know what kind of questions they give you now in more advanced exams in the UK, such as STEP, AEA, and so on. I think these are more likely to come up in American exams, some of the specialist American exams, or Australian exams. There's a couple of fairly decent qualifications down there. We're going to try to, first of all, some thoughts other than quitting. Clearly, we need to put these two Arctans together. I have one advantage over the typical student. I'm aware there are identities, inverse trig identities, which allow you to put inverse trig functions together. I have, in fact, a mathematical book of formulas. It's actually pages and pages, very fat, that has all sorts of things. And if I needed that for myself, I could just go and look it up. I don't remember what's the arctan of A minus the arctan of B identity. Perhaps a long time ago I used to know it. So now I'm going to have to derive it. That's the painful thing. And if I make a mistake or I fail, you feel free to laugh at me. Okay, this is what I'm going to do so we can all follow. And also so I can actually do it, because my brain is not working very well at this moment in time. I'm going to say this is A and this is B. When we're having inverse trig functions, think of them as angles. It's the best way to actually manipulate them. So that's the angle A, or theta and phi, and that's the angle B. So I'm trying to find an expression for A minus B put together in some kind of arc cos, arc sine, or whatever. So let's write up here something. A minus B, this angle minus this angle, is definitely going to give me another angle. Call it C. Because I've got arctans for both of these, it would have been a nightmare if I had an arctan there and an arc cos in there, for example. Not that it would have ever come from an integration, but let's suppose. I'm going to tan this equation. So the tan of A minus B is equal to the tan of C, most definitely. And of course, that's compound angle from A level, tan A minus tan B over 1 plus tan A tan B. Oops. And that's equal to the tan of C. Okay, so far. So what is the tan of C? Let's switch pens. I'm going to write the tan of C on the left, somewhere here. And start thinking about this tan of A. What the hell is tan of A? The tan of A is the tan of this. But that's an arctan. So the tan of the arctan of this. So that's going to be 1 plus alpha over the square root of 1 minus alpha squared. That is the tan of A. Minus the tan of B. Minus, my B is this. And therefore the tan of the arctan is this. So that is equal to alpha over the square root 1 minus alpha squared. That's the numerator. And of course the denominator is very easy, because this actually repeats, so I can just write them again. So that is, of course, that times that. So this is, in fact, what will happen. It's going to be this times this will kill the square root. So it's 1 minus alpha squared. That's the first thing that happens in there. And then that times that will give me an alpha plus alpha squared. Careful, there's not a minus in there. I'm just multiplying these two quantities. Okay, that's the tan A, tan B. Let's tidy this up a little bit. what will happen? The tan of C is equal to 1 plus alpha minus alpha is 1 over the square root of 1 minus alpha squared. And on the denominator, God, this is actually very, very painful. 1 minus alpha squared plus alpha squared over 1 minus alpha squared. Something distant cancels, yep. So we got that. And I'm running out of board space. So let's make some room. I'm going to go to the very top. And this, what I've got there so far, that's the tan of C, that's the tan of C. So let's write again. The tan of C is equal to, and this will give me now 1 over the square root of 1 minus alpha squared. That's that bit there. And this is going to be 1 plus alpha. 1 plus alpha, I have to be careful I don't make mistakes here, over 1 minus alpha squared. That's this bit here. Some of this will cancel, so if I write it as, move that to the top, I'm gonna have to put the extra work in, so I'm getting very tired. I don't want to make a mistake at this stage now. That goes to the top, and at the bottom I have 1 plus alpha and 1 minus alpha squared. Still need more room. I hope some of you are still with me and you're still enjoying the beating of the question, but it'll be a lot of satisfaction when it's done. And I can definitely say who's laughing now, because the question is actually laughing at me right now, honestly. I missed the square root somewhere in all of this. Let's have a look. Where's the square root? Which I missed. It's at the bottom. That's this is the half. Okay, so now I'm gonna have on the top, I have 1 minus alpha squared to the half. That cancels that and it goes to the half over 1 plus alpha. And at the bottom, this is a difference of squares, so it's going to be 1 minus alpha to the half, 1 plus alpha to the half over 1 plus alpha. And believe it or not, this is actually, it's a little bit semi-tidy compared to what I was thinking it might turn out to be. This now cancels that, but it will leave me to the half at the bottom. So the final answer for this is the square root of 1 minus alpha on the top over the square root of 1 plus alpha at the bottom. And we have to make sure we understand what we just found. That is the tan of C. What is C? C is that minus that. So in fact my C, which is A minus B, is the arctan of the square root of 1 minus alpha over 1 plus alpha. I need to change pen, because this pen also died. That's how long this question is. So I have this expression for my integral, and this quantity turns out to be this quantity. Hopefully no mistakes. Okay, this is equal to this number at the front, 2 over 1 minus alpha squared, and the simplification of that is the arctan of the square root of 1 minus alpha over 1 plus alpha. Okay, better from here to here, but not quite what we need. So we really need to show that this quantity here is the same as the arccos, basically, of alpha. This, of course, we already have. So there's more work to do with inverse trig functions. Okay, need to think. I think that's a lot better. I mean, that is not actually a lot more standard. That doesn't scare me as much as the previous one did. So let's think how we're going to do that. We need to somehow show, just looking at this bit here, I'm going to write it up here, so I need to understand what I'm trying to show. Two lots of the arctan. I'm trying to show two lots of the arctan of the square root of 1 minus alpha over 1 plus alpha is the same as the arc cos of alpha. Okay, I think I'm going to start with an arctan. So probably better to say the following. Put the half here. Okay, so I'm going to do that on the side here and then just finish off. I assume that we're going to get to the right thing. So this is what I'm trying to prove. And if I prove that, that will give me the answer. Let theta, so I'll use theta because theta was part of the problem. Let's not use theta because theta was one of the variables on the substitution. Let's say we call psi. Let psi equal to the arctan of this quantity. 1 minus alpha, 1 plus alpha square rooted. Quite clearly, I'm going to take tans both sides. Tan psi is equal to the square root still of 1 minus alpha over 1 plus alpha. Square both sides. Tan squared psi is equal to 1 minus alpha over 1 plus alpha. Do I want to draw a right angle triangle for this? What am I trying to go? I'm trying to go to an arc cos of alpha. So I need causes. Causes, I'm going to go from sec squared. So what I'm doing next is 1 plus tan squared of psi is 1 minus alpha over 1 plus alpha plus 1. I've just added 1 to both sides of this equation. That, of course, was my intention, to create a sec, and then from a sec I'm going to go to cos, and from a cos I'm going to go to an arc cos. Okay, so we have the sec squared of psi is equal to, we need now, what do we need to put them together? 1 minus alpha plus 1 plus alpha, 1 plus alpha, which on the next line this will cancel, so that is a 2 over that. So cos squared of psi, cos squared of psi is equal to, I'll turn it upside down, so it's going to be 1 plus alpha over 2. I don't want to square root because this is going to be a pain. That will never give me that answer. So what's the alternative to that? The alternative to that is kind of obvious. I need to double both sides. I'm going to put 2 cos squared of psi is equal to 1 plus alpha, and then I'm going to subtract 1 from both sides. I'm going to do it here. Sorry, I switched pens. My black seems to be dying as well. This question has been quite lengthy. I'm going to subtract 1 from both sides. Can you see what I'm doing and why I'm doing what I'm doing? Because I've gone to silent mode because my brain's like mush at the moment. I subtracted 1. So when I subtract 1 from there and there, that gives me alpha. And now I think I begin to smile. This is now identity. That's of course the cos of 2 psi, and that of course is equal to alpha. 2 psi is equal to the arc cos of alpha. Psi is a half arc cos of alpha, and of course psi is my arctan. So the arctan of the square root of 1 minus alpha over 1 plus alpha, this quantity here, is indeed this quantity. And therefore, when I substitute it in, arc cos of alpha, and when I substitute it in, this of course will give me 2 over, it gives me a lot of pleasure now to copy it, otherwise I wouldn't have bothered. I know it's correct, but it's the final moment of glory. And the arctan is of course a half arc cos of alpha, 2 times a half as required. This was quite a beast, quite long. It really has drained me, and I think I need to lie down after this. I'm definitely laughing now, and I hope you learned an awful lot from this. I'll see you very soon. Bye for now.